This is a nice problem worth going over, and I'm going to go over the whole thing pretty quickly. And when I wrote this, this was the 1,080,503rd question that was written for WebAssign. It's interesting that there are that many questions available on WebAssign. That's what this unique identifier is. Well, here we go. We've got some sodium hydroxide. That's the classic strong base. And you're going to find sodium hydroxide on the AP exam somewhere. If you don't, you've got a fake test. Okay, here's some correct answers for it, but let's just check and see how they were gotten. We've got 0.76 grams of sodium hydroxide. Okay, 0.76. And the molar mass of sodium hydroxide this is the exact one. I use 40.0. It's an easy one to remember. Sodium hydroxide is used so often. 40.0 will give you 3 significant digits, so that's what I use. I can use the 40 right here, so I don't have to type in quite as many numbers and have a chance of getting it wrong. And indeed, that's how many moles. That tells us really how much sodium hydroxide in there. It's in 475 milliliters, so I'll divide that by 0.475 liters to get concentration. Moles divided by liters in constant gives you molar concentration. And indeed, perfect answer here. If you were putting this down on an AP exam, you would include a couple more zeros here to show 3 significant digits. So this is a strong acid. 100% of sodium hydroxide turns into hydroxide ions. And so that's the nice thing about all the hydroxide solutions is that they become hydroxide ions. And indeed, here you can see this was done correctly, where we have 4 100ths, and again, I would use a couple of zeros. Now, the pOH was done nicely. Just take the negative log, which I've got here, of, I can put in the last answer, and enter that. And indeed, here's our pH of 1.40. That has 2 significant digits, but typically people write out pHs only to the hundredths value. It's really tough to find a pH or pOH meter that can do a better job than getting to the hundredths without doing a lot of calibration. Now, here's where the answer is incorrect, where we've got the pH of this. So let me quickly go to my outline. I've got it here somewhere. Just let me do a little bit of hunting here. And here on my screen, I'm going to quickly go to here we go. Important piece of data. This is worth looking up on the outline, and it's worth remembering. When you have 25 degrees Celsius, the pK of water is 14. So the pH and pOH will add up to 14. So you can quickly convert from a pH to a pOH by subtracting that number from 14. And don't forget the kW here, where if you have the molar concentrations, this is going to be a critical piece of information that, again, you'll end up using. And this is good for 25 degrees Celsius. If the temperature changes, then the kW changes, and then you've got some complications which are shown in this further reading on this outline. So let's go back to that problem and pull up my calculator, and we've got the pH, so I'll just do 14 minus my pH, second function answer, and there would be the pH. And that makes sense. We know that if the pH is greater than 7, it's a basic solution. And, 12.60 is what I'd write. That would be my value that I would write down, 12.0. Well, let me put that calculator up again because I forgot it already. 12.60 as the pH. To the hundredths, typically when you write a pH or pOH value. And so there we've got that. And now we're dealing with ammonia, which is a weak base. These things, weak base, we've got an equilibrium value here, which indicates that it doesn't completely convert into, in fact, actually what I'll do, I'm going to go back to this problem and change it and show, oh no, I've got it here. Here, I've got the arrow indicating this is a 100% reaction. And in this case, it's not 100%. In fact, it's not nearly that amount. Now, we've got a pH of ammonia at 10.3, and that's where we go back to our comment that we had before, where we know the pH and pOH add up to 14 unless we've got a weird temperature. And we'll go back and say, okay, we've got a pH and we can find a pOH. Now, so I'm going to take 14 and subtract that 10.93. That is a basic solution, not as basic as our Drano, which was at close to 13. This is 100 times less. Make it, 10 times less concentrated in terms of hydroxide ions. And there we go. We have a pOH of 3.07. Remember, a lower p-value means you've got more of the stuff. So there we've got our pOH of 3.07. Now we want to know the concentration of the hydroxide ion. Okay, well, we've got the pOH, so I would go second function log. We're going to go anti-log, put the negative back in, and again, I'll use my previous answer. And here, we've got a concentration that is 8.51 times 10 to the negative 4, or 8. I would, for Webison, I'd use all three values, three significant digits. And so let me get my calculator out. Oh, I've got some answers to put in. There we go. Get my calculator again. That was 3.07. So 3.07 was our pOH. And now let's see what the hydroxide concentration is. Well, again, out of my calculator, I did that. I did the anti-log. 8.51 times 10 to the negative 4. 8.51 times 10 and negative 4. And of course, this is in molar. They've got the molar written for us, which means we don't have to write that down for our arrangement for our answer in WebAssign. Percent ionization is pretty important too. And this is going to be easy to get because it's just the hydroxide that we just figured out over the initial concentration. And let's see, did they give us the initial concentration? Yeah, here it is, 0.04. So I let my calculator out, and I've got my hydroxide concentration in there already. That was the 8.51 times 10 to the negative 4. So all I've got to do is divide that by the given concentration, which they had to give us for us to figure this percent ionization, and that was 0.04 times 100, and there. Only about 2%. I mean, that's sort of interesting, but that's typical for weak substances. We have this 4/100 molar, which is typical for an ammonia solution, but of that ammonia, only at any given time, only about 2% of that ammonia is producing hydroxide ions, which is good because you don't want to have a cleaning solution that's going to be caustic. We just want it to be caustic enough to get rid of dirt. So again, this would be, we'd have a percent that I can put down, if I would have remembered it, as 2.13. Interesting enough, I should have been here. 2.13%. And is that percent in there? Yeah, that's written on the WebAssign as our unit. That's typical for weak acids and bases. The more dilute it is, the greater the percent ionization, but it doesn't make up for that dilution. So there we've got our answers. Okay, I'm stopping and posting it. Thank you, Jack, for posting this. I think this is going to help some students.